Now we consider the case for a metal semiconductor junction. For a metal semiconductor junction, the semiconductor has an electron affinity, but for the metal, it's called a work function. The work function tells you similar information as the electron affinity. The work function tells you exactly how much energy it takes to remove an electron from the Fermi energy level of the metal. And so it effectively tells you where the Fermi energy level is relative to the vacuum level. So when I draw I would approach this similar to a heterojunction where I would draw my band offsets. I draw my vacuum level as flat. On the left side is my palladium in this example. And I draw my work function or my metal Fermi energy as 5.6 eV below my vacuum level. Then on the right side where I have my silicon, because I know my electron affinity is 4.05, I draw my conduction band 4.5 eV below my vacuum level. And then my valence band 1.1 eV below my conduction band. And when I do that, I get this as follows for my band offsets. Now for a metal, the metal likes to pin the Fermi energy level to its work function. And so what you do is you assume the Fermi energy level is flat with the work function of the metal as such, as it extends into the semiconductor. Remember that the pins all stay the same. The relative levels at the interface always stay the same. It's pinned that way, right? Then once I have my Fermi energy level, I can draw my flat band region. I want to make sure that I draw the width of my flat band region. Draw the band gap of my flat band region equal to that of the band gap I drew at my interface. So I want to make sure they're about the same width here. And I want to make sure I'm drawing this flat band region away from my interface. It's p-type, and so therefore I'm going to draw my valence band close to my Fermi energy level as such. Then once I'm done drawing my flat band region, I can then connect my flat band region to my pins as such. And then once I do that, I can clean it up. And what I can see here is I've created, as you can see here, this shape as such in my energy level. Now, this is a p-type silicon. So we know this is a p-type contact. All right? And so what that means is that what it's going to be moving is mostly holes, not electrons. And so I'm going to look at my valence band. I'm going to say, okay, if I'm a hole trying to move from my semiconductor to my metal, do I run into an energy barrier? And the answer is no, right? I can see that I can easily move from this energy to that energy because this energy is more electropositive than that energy is, right? So I can move from here to here, and vice versa. I can move from my metal into my semiconductor. And so because I am not rectifying, because I don't have a large energy barrier for my holes, I can consider this a p-type ohmic contact. All right? And this will be it. Now, consider this example where now I have gold in N-type gallium arsenide. Again, I'm going to do all my pinning like I did before. My work function is 1.5, so I'll bring it down here. And my electron affinity is 4.07, and then my band gap is 1.42. Now I'm going to set my Fermi energy level according to the work function of my gold, and I'm going to draw my flat band region. I know it's N-type, and so I'm going to draw my conduction band close to my Fermi energy level. Then I'm going to connect my flat band to my pin conduction levels, pin energy levels. And then once I clean it up, I can see that for electrons, because this is N-type, so I'm considering electrons, for my electrons to move from my semiconductor to my metal, it has to go up a ramp and then over. So that's a small barrier. But then for it to go from my metal to my semiconductor, there's a huge barrier, as you can see, to go from this level up this wall and over this peak right here. And that is my Schottky barrier. So I can call this an N-type Schottky contact. it's going to be rectifying 4 electrons. All right? Now, I want to show what this looks like. To show what this looks like, you have to consider a bias. Now, we'll go over this in another lecture, but what does the bias do? The bias changes my relative Fermi energy level. It changes my work function, in this case, on the metal. All right? And so, I'm sorry, not work function. It changes my relative Fermi energy level to the work function, right? And so, with zero bias, it means that my Fermi energy level on my semiconductor side is equal to that of my work function. However, if I apply a positive bias on my metal, that means that now my work function is now plus 1 volts worth of electropositive more than my semiconductor. That means that I would draw, because things are pinned, I'm not going to change the way my work function on my metal. I'm not going to do that because everything is pinned. What I'm going to do is I'm going to say, okay, if my work function on my metal is now more electropositive compared to my Fermi energy level, then that's the same as saying my Fermi energy level is more electronegative compared to my metal, right? And so, based off that interpretation, I would take this plus 1 bias on my metal and then use that to shift my Fermi energy level more electronegative on the semiconductor side. And so now you can see that my Fermi energy level is now more electronegative than my work function. Or my work function is more electropositive than my Fermi energy level. Remembering that electropositive is towards the bottom and electronegative is towards the top, right? Now that I have my new Fermi energy level and my bands are pinned, what you see here, this is what I had at zero bias. Now, I'm going to draw my flat band here and then reconnect. And what I find is now the shape of my band bending has changed significantly. All right? And you can see that my electrons have no problem moving from my semiconductor into my metal. Right? You can see the electrons just move right on over. No problem whatsoever. Okay? Now, if I apply a negative bias, that would mean that my Fermi energy level is now more electropositive compared to my metal. And so what I would do is I would shift my Fermi energy level further down or towards electropositive relative to my work function, my energy of my metal, as you can see. Once I've shifted my Fermi energy level down, I do the same thing. I draw my flat band region and connect. And when I draw my flat band region and then connect, you can clearly see that the electrons that are sitting in the metal, which want to move into the semiconductor, right? Because I apply a negative bias to my metal. So it wants to move into the semiconductor. Hits a Schottky barrier wall. Hits this wall and gets reflected back. And so the electrons don't easily flow from my gold into my semiconductor. But electrons can easily flow from my semiconductor into my gold. This is what happens depending on which metal and work function you use. And this is why the particular type of metal you use is very important when you determine the type of contact you end up with. Whether you end up with an N-type Schottky, N-type ohmic, or P-type Schottky, P-type ohmic.